Hello everyone, welcome back in the course of higher surveying. Today is our last lecture. We are concluding what we have learned in the last 35 lectures. So, whatever techniques and subjects and the logic we have learned in this course, we are going to use it to solve the problems that we have raised in our first lecture. I hope that you remember all those problems. Let us go ahead. These are the 10 modules we have discussed in this course. So, they have contributed to 35 lectures. Now, let us start that what we have learned in different modules. So, in module 1, we developed the appropriate context of this course, higher surveying. We have taken some real life projects, for example, forest study, and then we see that how the basic surveying can help us. Then we realize that there are many limitations of the basic surveying, and as a result we need some better techniques or technology or some better facilities. So, we concluded that we need something else to address all those real life problems. Once we started looking to the real life problems, we realized that these problems are not resolved that easily, and as a result we call them the research projects, because many of the things are unknown or many of the studies has to be conducted first to understand requirements of the projects. Finally, we have concluded that to do these real life projects, we need some kind of techniques which can acquire the 3D data, and 3D data should be highly accurate. At the same time, we should have very high coverage. Moreover, we should acquire the data in a minimum time. Then we discussed the module 2. In module 2, we talked about the coordinate and reference systems. We have first defined the reference system, reference frame and coordinate system. Then we say that the reference frame is the realization of the reference system definition, and coordinate system is a mechanism of defining 3D coordinate or maybe 2D coordinates of a point in a given reference frame. So, then we discussed what are the type of reference frames, and then we learned the coordinate and datum transformations. That means how to convert the coordinates from one coordinate system to another and how to change the datum or the reference frame. Later we learned the map projections, and we said that why map projections are relevant in some of the cases, especially the navigation. Then we finally defined what is the International Terrestrial Reference Frame, ITRF, and that is originated from the concept called International Terrestrial Reference System, ITRS. In the module 3, we discussed about the astronomy and time, how astronomy and time are connected. We have defined the astronomical reference frames, and then we have discussed that how to conceive a concept called ICRF or International Celestial Reference Frame. Using ICRF, how to connect the ICRF and time to ITRF, and how to find out the definition of ITRF with the help of ICRF, and how to update the ITRF continuously based on the observations of the ICRF. Also, in addition to that, we have seen the applications of the astronomy and time, and that was a kind of module that appears to be little off the course. However, it is very relevant if you are a student of higher surveying. Then we move to the module 4. In the module 4, we realize that if we have lot of data, that means we have redundant data for a given problem, we should extract the useful information. To extract the useful information from redundant data, we realize that we need to use some technique that can do some kind of adjustment process. That means adjustment of the observed data, and after the adjustment process should reveal the useful information and what we call as parameters. Then we realize that the least squares solution of a problem can extract the useful information or the parameter values by adjusting the redundant data. Then we learned what are the types of least squares method that is possible with the computer to write our own codes, maybe in Python or any other IDE. And that was the turnaround point for us to understand that how basic surveying is different from the higher surveying. At the end, we have also talked about the quality of the parameters or the extracted information that were derived from the redundant data. Module 5 discussed the global positioning system. We have discussed the additional information in one lecture. In module 6, we have discussed a lot about the photogrammetry in 8 lectures. So, after introduction to the photogrammetry, we have discussed vertical photogrammetry, stereo photogrammetry and analytical photogrammetry. Then we have realized products of the photogrammetry: digital elevation model, digital terrain model, the ortho map. Remember, ortho map is not the topographical map. The topographical map contains some information in the form of some features, but an ortho map contains the color information or the image information as well as the planimetric coordinates of a map. That is why ortho map is much better than the topographic map. Then we have seen the digital photogrammetry. We learned how to calculate the derivatives, or how digital photogrammetry allows us to calculate the derivatives as well as the automatic processing of the data. Then we have seen the terrestrial photogrammetry or low altitude photogrammetry. We said that the distance between the camera and the object on the surface of earth has very less distance, and as a result we said that it is a close range photogrammetry. Then we have learned different protocols of the close range photogrammetry, and we have also seen that how to develop a 3D view of a given object using the overlapping photographs. Recently we have conducted one study here at IIT Guwahati, and then we realized that it is possible to generate highly accurate 3D models using the terrestrial camera or maybe drone camera. I can guarantee you that even you can create some kind of millimeter level accuracies in your work using terrestrial photogrammetry, and which is quite cheaper because you need only one camera of high resolution. At the same time, if you are working with the limited distance with the object, automatically you will have the high resolution, and from the high resolution achieving the higher accuracy requires some kind of research. So, if you do that research, you will realize that it is quite easy to get the very high 3D accuracy of the digital elevation model, and now you can prepare the 3D models of the buildings around you, or even you can prepare a good 3D map of your locality. Then we moved on to module 7, and that was LiDAR. LiDAR is a active remote sensing method or active remote sensing technology, and then we have talked about the LiDAR data acquisition, geocoding of the LiDAR data errors, and the data processing for LiDAR data so as to create digital elevation model, DTM, BEM and digital surface model, DSM. With this we realize that both photogrammetry and LiDAR can give highly accurate 3D data in terms of centimeter level accuracy if we are using them as a airborne method. If you are using them as a terrestrial method, even we can go for the millimeter level accuracy, though we have not discussed about the satellite based, but LiDAR is not available with the satellite platforms. Photogrammetry is available, and it is basically useful for the planimetric mapping only, because the B by H ratio for the satellite photographs are slightly different and the lower compared to the what we can achieve with the flexibility of the low altitude photogrammetry or terrestrial photogrammetry or aerial photogrammetry. The resolution is also very high in case of these three photogrammetry compared to the spacebound photogrammetry. Now we have realized that both technique, that is photogrammetry and LiDAR, are useful because both give the comparable results in the accuracy as well as the resolution. But we have realized that LiDAR is an active system and photogrammetry is a passive system. That is why they have some other disadvantages as well as advantages. At the end, we realize that both are complementing technologies, not competing technologies. They do not compete with each other because of the different capabilities. I can complement one technology with other. That means if I use the 3D data from LiDAR, if I use the photogrammetric information from the photography, then I can equip the two things and I can generate 4D information, 3D for the 3 dimension and the 4th for the color information. So, this was the kind of integration aspect of the two technologies we have discussed. Module 8, where we discussed about the radar, which is quite a different technology because the microwave region is sensitive to the material, unlike LiDAR, and that is the reason it can give multiple advantages. First is topographic mapping in certain region of microwave spectrum, and in certain another region of the same microwave range, we can use the frequencies to measure the type of material. In certain region, the microwave is very sensitive to the material, for example, vegetation or soil moisture. So, we can have the different studies based on the selection of the wavelength, and that is why radar has multiple applications and wide area of applications are available. On the other hand, we saw that radar is basically limited by the resolution, and because of the low resolution it can be used for very large scale studies, for example glaciers, where the resolution of the centimeter level is not useful because the glacier movement are itself is in the level of meters per year. So, over a year duration glacier moves by couple of meters, let us say 18 meter, 20 meter or maybe sometimes 80 meters, and that is what is happening in Himalaya. So, there we realize that for such a study radar is much useful compared to photogrammetry or LIDAR. But at the same time photogrammetry and LIDAR can be used if high resolution studies are required. In the radar we have discussed about the geometric aspects, radiometric aspects, radar grammetry, interferometry, differential interferometry, and finally we saw some different aspect of the radar, which is dielectric aspect from the geological perspective. And then we realized that if we use the dielectric information of the material, under certain circumstances I can find out the depth of the layers or the subsurface investigation can be performed. So, that was our module 8, and then we moved to module 9. It was all about the hydrographic survey. So, we defined what is the hydrographic survey, and then we said that how to perform the hydrographic survey using conventional and modern methods. Then we discussed about the echo sounders, and in the whole process we have defined a term called sonar. Sonar is a term that stands for the sounding, navigation and ranging. Like LIDAR, like radar, we have sonar. Then we see that how to perform the airborne LIDAR survey to find out the depth of the water bed or the sea bed. Then we discussed our module 10, that is about navigation. Navigation includes all the output of many technologies, and that is why we have discussed the navigation as a last module of this course. We first defined what is navigation. We have then classified different type of navigations. Then we have seen different system of navigations that are available today and they are in use. Then we have seen the application of the navigation by a forest study, where we have used a GPS in order to reach to a ground control point that we want to collect in the field. Finally, today we are concluding. Before conclusion or before completing this lecture, let us look into the studies again. So, have we responded to these studies or have we responded to the requirements of these studies using these technologies? So, first was the forest study. In case of forest study, we wanted to find out what is the area of forest in country today. So, you can use the radar or you can use LIDAR or photogrammetry to find out this information. If you use radar and the radar frequency is sensitive to the vegetation material, you can give better answers to the large scale study related to forest. So, all these answers can be responded using either of the technology which I named here, like radar, LIDAR or photogrammetry. Then we have come to the solar study. So, for example, what is the position of sun at 10 o'clock in morning at rooftop of house? So, all this can be responded well if you have sun algorithm available to you, and sun algorithms can be used which are freely available. Later on I wanted to find out that whether sunlight will be available at a certain place or not, that can be derived using sun algorithm and the available 3D data of the 3D structure. For this data we can say that both LIDAR and photogrammetry are much useful compared to any other technique, because they provide highly accurate 3D data, and to find out that availability of the sunlight at the rooftop at a particular time, I need to have highly accurate 3D data so that I can find out the shadow of one building onto another, and that is the reason I prefer to use LIDAR or photogrammetry. Similarly, all other questions can be responded. So, if we have sun algorithm, time measurement and 3D data of high accuracy. Then we discussed about the town planning. In case of town planning, which technology should be used? So, if I have coarse resolution requirement, then I can use even the photogrammetry or LIDAR, but at very low resolution, or at the same time I can use radar if the studies are to be done at coarse resolution or to understand the terrain. Later we can use the highly accurate technologies like LIDAR and photogrammetry to develop some other aspects, for example some building development. Then we talked about military intelligence. Then we talked about the bullet or metro train project. Remember, in case of bullet or metro train, the metro train can pass through tunnels or it can pass through underways. So for that purpose, I should use a photogrammetric drone or LiDAR with a drone. Moreover, I would like to confirm that the technologies like total station will also be useful, because in case of underways, we should minimize the chances of accidents. So in case of use of UAVs, there could be some chances of accidents, and therefore even such places where metro passes through underways or overways in a city which is highly populated like New Delhi or Mumbai, we should use the terrestrial technologies like LiDAR, that is terrestrial LiDAR, or terrestrial camera, or the total station. Alright, so there we can develop a good infrastructure using the 3D data, and I can respond to all the questions here. But in case of bullet train between the two cities, for example, between the Ahmedabad and Mumbai, we can conduct even the airborne surveys for LiDAR or photogrammetry. Accuracy requirement would be quite different there in the centimeter level, and these can be fulfilled with the help of LiDAR or photogrammetry, especially the airborne one. Then we discussed about the mining of the coal field. Here I would like to say that what should be an appropriate technology? Areas are most of the time waterlogged, or areas are sometimes having coal fires. So that's why photogrammetry will be much useful here. Moreover, with the low altitude photogrammetry, one can achieve very high resolution. Further, these can be identified with the help of LiDAR also, but photogrammetry will be more appropriate, or combination of LiDAR and photogrammetry will be the most appropriate. In case of glacier, we have already said that radar is much better than the other technologies, because radar is sensitive to the large scale study where we believe that glaciers are melting at much higher rate. That means if glaciers are moving at the rate of 18 meters per year or 80 meters per year, no doubt radar is much better technology, because it provides resolution of couple of meters. And finally, if you estimate the velocity, what will happen, that velocity will be of order 5 to 6 meter error, and that is well acceptable if the movement of the glacier itself is 80 meters in a year. However, LiDAR as well as photogrammetry can also be used in terrestrial mode, airborne mode, or low altitude mode. But in case of low altitude mode, it is dangerous to use the drones over the glacier, because the glaciers are not habitable places, and there are a lot of dangerous situations that come across while we are performing the survey, and that is why radar is useful. However, we can use the photogrammetry with very expensive drones or with expensive terrestrial LiDAR scanners. Expensive LiDAR scanners provide almost 5 kilometer range, and that is why it is much useful from a distance where you can see the glacier, so that you can map the glacier completely. And so if you perform this study every year, you can find out what is the loss of the glacier ice over a year or maybe every 6 months, and you can quantify this loss of ice at very high resolution. So next is the other studies: dam surface monitoring, landslide subsidence, high-rise structures, mobile signal strength, and sound propagation. So all these studies can be handled with very high resolution data only. For example, dam surface monitoring, we should use terrestrial LiDAR, we should use photogrammetry. Similarly, in case of landslide subsidence, even we can use radar, but landslide should be a regional landslide, not the local landslide. In case of local landslide, the effect of landslide is very small, as well as the area of landslide is very small, and hence we should use the low altitude photogrammetry or LiDAR, because both of these technologies will provide very high resolution data, and we need the high resolution data to understand small intricacies of the landslide which happened in very small local area. Similarly, for high-rise structures have planimetric area small, and hence we need some technology like LiDAR or photogrammetry. Finally, mobile signal strength mapping, that can be handled with the coarse resolution data, but photogrammetry and LiDAR will be very useful to map the whole city, and then we can find out using the 3D models of the city that how mobile signal is propagating with the available 3D structure and how the strength is varying. Finally, sound propagation is just like mobile signal strength, but it has different aspect. So now, with the end of this lecture, I can conclude hopefully that the technologies discussed in this course can provide highly accurate 3D data for a certain research purpose or some real life project. At the same time, these technologies have very high coverage and they acquire the data in minimum time. So these technologies are really capable of acquiring the 3D topographic data. So with this, I would like to say one more thing here. Do these technologies have some limitations? Of course they have. And we should understand these limitations of the technologies by their accuracy limitations, by their resolution limitations, or by their use for a certain purpose. I hope that we have discussed enough amount of material to improve the content of the course. I would like to have a feedback from all of you. So being the audience or being the student of this course, you may provide an important feedback. So your feedback will improve the course in future, or I may add some more material if required. So finally, today we conclude our course on higher surveying. I hope you enjoyed this course and the information shared in this course was very useful to you. Thank you very much.